Data center design is an exercise in mitigating physical and electrical entropy. You are building an environment engineered to never, under any circumstances, fail. The enterprise target for high availability is an uptime of 99.995%. That translates to less than 26 minutes of allowable downtime across an entire year. Hitting that mathematical margin of error is impossible if you rely on a single engineering discipline. To achieve true enterprise-grade resilience, engineers have to synthesize three highly distinct, heavily regulated industry frameworks into a single facility. First is TIA 942, governing telecommunications topology and physical spatial geometry. Second, Uptime Institute tiers determine mathematical formulas for mechanical redundancy to tolerate faults. Finally, ISO 27001 governs information security, wrapping the hardware in strict documented human protocols. To see exactly how these three practices intersect in physical reality, we need to construct a theoretical facility from the ground up, starting with the empty space. Long before a single server is racked, TIA 942 establishes a strict hierarchical infrastructure. It organizes the facility into specific, interconnected zones to ensure predictable data routing. Looking at this 3D layout, the point of origin is the entrance room. This is the heavily fortified demarcation point, where external provider lines, like municipal fiber networks, actually breach the building's exterior. From there, heavy trunk cabling routes directly into the main distribution area, or MDA. You can think of the MDA as the core switching center for the entire facility. The architecture then branches outward. Fiber runs from the central MDA out to horizontal distribution areas, which serve as localized network hubs for specific rows of servers. Finally, those lines terminate at the equipment distribution areas. This is where the patch panels connect directly to the active server cabinets. TIA 942 dictates that this data cabling must run entirely separate from the facility's power lines. If high-voltage conduits run too close to fiber optic or copper lines, the resulting electromagnetic interference will cause massive packet loss across the network. This layout also creates concentric physical security perimeters. By placing the main distribution area deep in the center, any unauthorized person must clear multiple security checkpoints before reaching the core switches. Beyond security and data logic, this strict spatial topology is required for thermal management. Dense server racks generate immense heat, and cooling them efficiently requires highly specific geometric layouts. This cross-section diagram shows the standard hot aisle, cold aisle containment model in a data center. Racks face each other, drawing cool air from outside aisles, passing it over the hardware, and venting exhaust into a sealed central hot corridor that gets pumped back to the AC units. TIA 942 perfectly structures the physical nervous system of the facility, but a layout of cables and empty racks is entirely inert without a resilient way to deliver massive amounts of electricity. That brings us to the Uptime Institute standard, which governs mechanical and electrical availability. While TIA dictates where things go, Uptime dictates how those things perform under stress. It is a system built strictly around fault tolerance. This diagram shows the baseline requirements for Uptime Tier 1 and Tier 2 facilities. Power flows in a single active linear path, from the utility grid through an uninterruptible power supply and into the server load. The vulnerability here is obvious. Because there is only one active power path, performing routine maintenance on a generator or a UPS requires intentionally dropping power to the servers. The enterprise standard begins at Tier 3, introducing a strict engineering requirement known as concurrent maintainability. To achieve concurrent maintainability, engineers must establish a primary power path and an independent alternate power distribution path running right alongside it. Now, when a technician needs to service the primary UPS, they can intentionally isolate it, taking that unit completely offline. The facility shifts the critical server load over to the alternate distribution path. The hardware receives continuous power without a millisecond of interruption. Tier 3 design allows a facility to operate indefinitely without any planned downtime. However, it still leaves servers critically exposed to sudden, unexpected hardware failures on the active line. In a mission-critical environment, the worst-case scenario is an unpredicted, catastrophic short circuit or component failure. A sudden fault drops the load instantly, before a human technician can manually switch over to a backup path. Protecting against spontaneous faults requires the highest level of the standard, Tier 4 fault tolerance. This requires what is known as a 2N active-active dual power path. In this topology, both independent pathways are constantly live and simultaneously feeding the server load at all times. If a component blows out on path A, there is no manual switchover. The active feed on path B continues to push electricity, instantaneously absorbing the load without any human intervention. Tier 4 also mandates deep physical compartmentalization. The primary and secondary power systems must be housed in completely separate fire-rated rooms, so that a localized fire or water leak cannot destroy both systems at once. Tier 4 delivers near mathematical certainty of electrical delivery. But installing this volume of complex hardware creates the ultimate vulnerability in any system: human error. You can spend $50 million building a mathematically perfect Tier 4 facility, and it will still immediately crash if a technician abruptly unplugs the wrong power distribution unit inside the rack. This is where ISO IEC 27001 enters the matrix. It serves as the internationally recognized governance framework for information security management systems, or ISMS. ISO 27001 doesn't care about cables or generators. It dictates the strict human processes, training protocols, and documentation standards that govern how people interact with the physical hardware. It starts by requiring standard operating procedures, or SOPs, which act as the documented baseline for every routine activity, from managing visitors to daily walkthroughs. For complex engineering tasks, it requires methods of procedure, or MOPs. These are highly specific, sequenced, step-by-step instructions that must be followed exactly when taking critical hardware offline for maintenance. And when the unexpected does happen, it mandates emergency operating procedures, pre-written crisis response blueprints designed to keep technicians from making impulsive decisions during an outage. This entire system relies on rigorous change management controls and unalterable audit trails. Before a technician can physically alter a server, a ticket must be submitted, risk-assessed, approved by multiple layers of management, and permanently logged in the system to maintain compliance. ISO 27001 also requires zero-trust physical access controls. Even if you work in the building, your badge only grants access to the specific zones required for your exact job function. Biometric scanners, anti-tailgating man-trap doors, and continuous video surveillance serve as the physical enforcers of these digital ISMS policies. Rigorous documentation and strict procedural adherence act as the binding agents. They are the only way to prevent human entropy from dismantling millions of dollars of TIA and uptime engineering. When you view a functional data center, you are watching these three frameworks operate simultaneously. TIA 942 provides the structural skeleton and spatial nervous system. The Uptime Institute tiers function as the resilient cardiovascular system, pumping redundant power and cooling through those concrete veins. And ISO 27001 acts as the procedural safety net, governing every human interaction inside. The reality of mission-critical engineering is that true 99.995% high availability is never achieved by simply purchasing expensive hardware. Designing a best-in-class facility requires a continuous, rigorous alignment across structural topology, mathematical redundancy, and human operational procedure. Internalizing this tripartite matrix is the absolute non-negotiable baseline for anyone designing, operating, or auditing modern critical infrastructure.